everyone. This is lesson 5.4 on medians and altitudes. Now, medians and altitudes are the next two types of segments in triangles, and their points of concurrency. The median's point of concurrency is called the centroid. The point of concurrency of the altitudes is called the orthocenter. So today we're going to use properties of medians and altitudes and their points of concurrency to solve problems. So here you have the diagram that represents a triangle and AH, so segment AH, BJ, and CG are called medians of the triangle. So the way a median works is that they join the vertex of the triangle and then the opposite side's midpoint. So J, G, and H are all midpoints of the triangle, as denoted by the congruent markings here. So if these two segments are congruent, then J would be the midpoint, right? And then the difference between this and perpendicular bisector is that the medians won't necessarily be perpendicular. Okay, maybe if it's isosceles, then one of them will be perpendicular, or if it's an equilateral triangle, then they'll be perpendicular, but they won't always be perpendicular. Okay, usually not. So a perpendicular bisector and medians, they can overlap, but not always. Now the point with the medians is that they go through the vertex. And that brings me to one of your what do we call it? Venn diagram, spreadsheet, the assignment that's due on Friday, the special segments and points of concurrency in triangles. So one of the things on there says vertex as endpoint, question mark. So you might be wondering what that means. That means does the perpendicular bisector, angle bisector, median, or altitude go through the vertex of the triangle? Okay, you could say yes or no, or maybe even sometimes. So with an angle bisector, obviously that's going to go through the vertex because it's an angle bisector. Medians go through the vertex, and we'll discover whether altitudes do or not. Perpendicular bisectors won't always go through the vertex, so you would want to put no for that one. Okay, so I'm going to do a little demo for you in the GeoGebra. So here we're going to make a triangle. And if you want, you can follow along. This one's called, this is just called Median by Jill Casey. You would just search medians and GeoGebra. So we're going to make a triangle it has to be acute and scalene. And I don't know if that's, let me do a better one. All right, that looks a little bit more scalene. So next what we're going to do is use the point tool and the midpoint. So since medians go through the midpoint of the sides, then we're going to make midpoints here. So tap the vertices and it will make the midpoint. Okay, and then we're going to take the segment tool and do a segment. And so the way that the medians work, once again, is it goes through the vertex. So you click the vertex and then the midpoint of the opposite side. Vertex, midpoint, vertex, midpoint. Okay, so then the point of concurrency is called the centroid. So for our centroid theorem, let's go back to this page. The point of intersection of the medians is called the centroid. Okay, so then the centroid theorem says that, so here's a special property of the centroid. The centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. So basically, point N breaks the three medians up into a ratio of 2:1, or that would be 3 parts total. So, for example, if GN is 2, then NC would be 4. Okay, because then total would be 6, and that would be for 6, which is 2/3. So Careful though, it says that the centroid is located 2/3 of the distance from each vertex to the midpoint of the opposite side. So from the vertex to the midpoint, it's 2/3. So the longer segment starts at the vertex to the centroid. So I'm going to highlight all of the longer segments here in purple. So this is the 2/3 segment. This is the 2/3 segment. That's the 2/3 segment. And then I'm going to highlight the 1/3 segment in green. So CN, NH, and NJ are the 1/3 segment. All right, so you're going to have to do a little math with the 2/3 ratio to figure out depending on what you're given. So here, if these are all medians, then AN, the distance from A to N, is 2/3 of AH. CN, or CN, here's CN, it's 2/3 of the whole thing, CG, and then BN is 2/3 of the whole median. All right, so let's do an example here. So you've got a triangle, so you have medians here because they go through the vertex and the opposite sides midpoints. And it says the RX is 48. So from R to X, that whole thing is 48. And then QW, so from Q to W is 30. Okay, so it wants us to find RW. Well, RW would be 2/3 of the whole distance. So if we broke 48, one thing you might want to do is consider the whole entire length. 48, if you divide that by 3, you get, 16? 16 times 3, it's early. Okay, yep, 16. So that means this would be 2 times 16, and this would be 1/16. So then RW would be 32. 16 times 2 is 32, and then WX would be 16. Okay, or you could do 2/3 times 48, and then 1/3 times 48 to get the 16. Okay, QZ. So notice that they gave us the 2/3 portion. So if 30 is 2/3 of the whole thing, then if you would want to divide 30 by 2 to get 15. So then each of the 1/3 parts would be 15. So then WC would be 15, and then the whole thing would be 45. 45. All right. So next we're going to talk about the altitudes. So, and also before I forget, I wanted to do another applet here. So this talks about whether or not the centroid can lie inside, outside, or on the triangle. So here, if it's acute, it will lie inside of the triangle. Let's try to make a right triangle here. So what happens when you create a right triangle? Well, the point of concurrency, the centroid, is actually on the right angle. Because, well, if you take point B, well, sorry, these are the altitudes. I'm sorry, I was going to say that doesn't really make sense. Medians in a triangle. Let's see if this one will. All right, yes, this is what we were looking for. Okay, let's try this again. So we've got the medians in the triangle, and let's try to make it a right triangle. All right, so the median stays inside the triangle. Let's see if we can make it an obtuse triangle. Okay, the centroid stays inside the triangle. All right, so no matter how we make it, the centroid is always going to stay inside of the triangle because it has to go through the vertex and the opposite side. So the opposite side is never going to go out of the triangle. Okay, so the altitudes. So here's your next diagram to draw. So JD, KE, and LC, the ones shown, are called altitudes. So imagine like you're riding on a plane, And the altitude technically is your distance from where you are and straight down the vertical distance downward, which would be considered, the perpendicular distance, because that would be the shortest. So imagine that you're at point K, riding in a plane. The altitude would be whatever straight down perpendicular. It's not necessarily going to be the midpoint. Okay, so look at point C and D. Those aren't the midpoints of JK and KL, but they go through the vertex and cross through perpendicular to the opposite side. So once again, these ones for the vertex as endpoint, you would say yes, because the vertex is an endpoint of one of the altitudes. So they are perpendicular segments that join a vertex and the line containing the side opposite the vertex. And then the point of intersection of the altitudes is called the orthocenter. Okay, so this would be called orthocenter. So let's take a look at the applet for that one. Actually, I kind of like how this one is, so we'll just go with this one. So try not to give away the answer here. All right, so we've got an acute triangle, and we've got altitudes, and the orthocenter lies inside. Now let's go back to our right triangle. So notice how as I make point A closer to 90 degrees, this altitude and that altitude, since they still need to be perpendicular, they're getting closer to that 90-degree angle. Because think about it. If you look at point B and it wants to go straight down, but that's at a right angle, then it's gonna go right on the side. Okay, same with point C. You kind of flip over the triangle. And if we make it an obtuse triangle, then those segments keep going further outside of the triangle. All right, so this vertex, the one at the obtuse angle, or this altitude, goes through the triangle, but the other ones are going to lie outside of the triangle. Okay, so for that one, you would know then what to put for the location. All right, so let's do an example here with altitudes. So find an equation of the line containing the altitude from G to FH. So if you want the altitude from G to FH, you would need to draw the perpendicular distance down. And well, since FH is horizontal, then the perpendicular distance is going to be vertical. All right, so here I'm going to go ahead and draw it in. And so the equation of the line, since it's vertical, is going to be x equals whatever it crosses through on the x-axis, which in this case is 2. So the equation here would be x equals 2. Find the slope of FG. So here's how we would find the altitude equation if it's not vertical. So what if it has some kind of slope? How do we figure that out? So FG, the slope of FG would be rise over run, and you're just rising up 1 over 1. So the slope is 1. Now, to get the altitude from point H to FG, it would be perpendicular, so then the slope would be the opposite reciprocal of this, which in this case is -1. So remember, if the slope is 1/2, then it would be -2 over 1, opposite reciprocals. Okay, so then the slope here, you would kind of go opposite, so up 1 over 1, up 1 over 1 to get a negative slope. And then you could draw in that line, which is what they tell you to do. So there's the altitude for point H going through FG. And part C says to find the equation of the line containing the altitude from H to FG. So then what would be the equation of this line? Well, for y equals mx plus b, it would have a slope of -1, and it goes through 1, 2, 3, 4, 5 on the y-intercept. So b would be 5. Oh gosh, kind of messing everything up here. Okay, so then the equation would be y equals -x plus 5. Okay, so that's how you can create the equation. You just figure out what the slope is of the point of the line that you're trying to intersect, and do the opposite reciprocal of that from the vertex point, and figure out what the y-intercept would be. Okay, And then to get the orthocenter, now whenever you want to find a point of concurrency, you technically only need to draw in 2 of the lines because then you'll find it. Now, if you're a little bit unsure, you might just want to go ahead and find the third one. If we did draw this third one, we would have to find the slope of GH. So that would be down 1, 2, 3, 4, 5 over 1, 2. So the slope of GH would be negative 5/2, which means that the slope of the altitude from point F would be positive 2/5. So if we went up 2 and over 5, 1, 2, 3, 4, 5, we do land at that orthocenter. So now we've kind of confirmed then that this point is the orthocenter. Now you don't really need to do a system of equations to find the orthocenter in this case, and I won't make you do a system of equations to do that, maybe for bonus question, but this is how you would find the orthocenter the basic way. Okay, so this would be 2 up 3. So the orthocenter is at point 2, 3. Okay, and next week I'm going to introduce you to a project where you'll find the points of concurrency of the altitudes, medians, angle bisectors, and perpendicular bisectors, okay, using coordinate geometry like this, okay? All right, so I think that's the end of this lesson. So you'll practice in the next lesson, and after that, you'll take a quiz on Friday. You do a quiz review on Thursday, and then quiz on Friday to prepare for your quiz. Well, the quiz review to prepare for your quiz. All right, so I'm going to stop talking. You guys have a great day.